So today I'll be giving a talk on the CMB cosmology and the Planck mission. And I thought I'd put in a couple of historical comments just because some of my old friends are here. And some of them might even remember this. Carlos just showed up. Simple, fast, one of which was very similar to what we were actually ending up with, but not exactly the same, and one of which was a radically different one. We were encouraged originally by the European Space Agency and other people to put in the FAST mission, and then there turned out to be a big political issue where the Economic Union was deciding that everyone had to join the European Space Agency. But if you had a space agency already in existence before that, then you could do your own missions and you could do small missions, and ESA would only do the middle-sized and large missions, of which Planck is considered a middle-sized mission, although you will see it is quite a large mission. And I should have realized that because it was 15 years before that I put in the proposal for COBE before it flew. So we're in a very similar situation. So I wanted to show you a little about this, the evolution, but one of the ideas that also happened 25 years ago, well, not quite 25 years ago, 15 years ago, we had a special cosmology conference, a CMB conference to celebrate the 25th anniversary of the cosmic microwave background. And I was charged, and this is like 1990, I think that's right, yeah, I guess it was 1990. So I was charged to give an after-dinner talk, which you should never do, to talk about what life would be like in 25 years. And in that, I proposed that one of the places I had just done a study, been on a study group to try about why people should be doing things from the moon. And my conclusion was, in fact, we should do it from L2, Earth Sun L2. And that actually turns out to be something that is coming into existence well before doing stuff on the moon. So here is the picture on the left of the COBE satellite, which was launched in 1989. The proposal was put in 15 years before that. And after the proposal was put together for what turns into Planck, although it wasn't called Planck at the beginning, a joint request for proposals was put in by NASA, and the idea was eventually they were going to be merged. But in fact, there were 3 separate proposals put in that were sort of the fragmented versions of that. One that became WMAP, which was the one that was selected, one that was called FIRE, and one that was a very fast spinner. And they competed, and we thought they were going to be merged, but in fact, WMAP went forward, and it was not merged with what became Planck. But it also did manage to go out to L2, and so you see on here the essence of L2, which I'll show you more about, where, whoops, there's the sun, the Earth, and the moon, and the satellite, which is out 4 times as far from the Earth as the moon is. And you'll understand why that is when I talk a little, if I get that far, when I talk about it. So here are the results. This is the top, the 4-year map from COBE. It's smoothed, spatially smooth, with about a 10-degree, effectively a 10-degree Gaussian. And prior to that smoothing, the best model of the galaxy foreground emissions is removed. And likewise, you see this is the WMAP data. And again, it is slightly smooth, but WMAP has much higher angular resolution. And the real reason is it's very similar in design to COBE, but instead of having just feed horns that looked out at the sky, WMAP looked through 2 back-to-back parabolic mirrors, which give it much higher angular resolution, and therefore gives more what's going on. However, you will notice things like this large cold spot, this large cold spot, this large cold spot. All those features that are on the large scale and the COBE map are reproduced extremely much the same in the WMAP. That is, if you smooth the WMAP or just take the low L components, subtract the 2 maps, it's perfectly consistent with noise. It's remarkable how good the agreements are. Okay, and just to take you back a little bit about where we were before WMAP, when we originally had COBE, we had, first the data points we had were COBE in 1992. It was just measured on what we call the Sachs-Wolf plateau. That is, we had a scale factor which told us the RMS level of fluctuations on the large angular scales, and we assumed that those fluctuations, the perturbations in the universe, were the same across there, and we had to put in the physics of the early universe, that is, the baryonic acoustic oscillations, and the transfer function for the radiation signal out into the present universe. And with that, you were beginning to suspect that there was the evidence of the first acoustic piece, and then later its harmonics, right? But it was 10 years later that we had the WMAP measurements, and you can see now the WMAP measurements going with fairly high accuracy through 2 of the acoustic peaks and the beginning of mapping out the third, and then a series of experiments, the best of which is Akbar, which are beginning to measure out the 3rd, 4th, 5th acoustic peaks. And that is the situation that we are in. And this is what gives us our standard cosmology of 2009, although it's actually, there are many new papers changing any cosmological parameters noticeably in 2009 yet, but so it's really 2008. But you can see the progress that we've been making over time, and this is sort of as a result of continuing to go on. So let me remind you about what we're talking about. We're looking out and we're measuring the angular diameter distance of objects on the sky. In this case, we're looking as far as we possibly can out to the last scattering surface, and we relate to the angular scale size a Legendre polynomial number, and the relationship's reciprocal, that when you get to reasonably small angles or large L's, that theta times L is basically equal to 1 radian, right? And so we then look at this last scattering surface where the photons have been scattering around, and the last scatter, we look at them and see what structures we see at the present epoch, right, that travel to us. So we have this relationship on the larger angular scales as a pi over L, then it goes to 1. And we then express what we see, because we're seeing the sphere around us. We're not seeing in 3 dimensions, we're just seeing the surface of last scattering. We express that in spherical harmonics, and it's a handy thing. We don't include the radial distance, just the spherical harmonics. And it's only when we want to do the 2-dimensional compared to the 3-dimensional that we have to include the Bessel functions and what's going on. And that these are our standard spherical harmonic functions that we do from the hydrogen atom, everything else in elementary physics. And the thing that we do, that's an assumption that we test, but has still to be tested more in the future, and is part of the last thing that Wayne Hugh was saying in his talk, was we assume that there is isotropy statistically on the sky. That is, there's no preferred direction in the sky and no preferred axis picked out on the sky. And therefore, we define an average over the ALMs for any particular set of L's. We average over the M's, and we call that C of L in terms of the temperature. Right? And that is the thing that we express. And we're able then to calculate using potential theory, that is potential energy theory, the angular power spectrum of the temperature variations. And those are the peaks that we saw in those curves predicted from our standard model. Right? And so where are we? Well, here is the data we have from WMAP, which gets us out to about L of 1,000 or 1,100 or so. What we're hoping to do with Planck is to improve the measurements through the 3rd peak on out towards the 7th peak with much smaller error bars, so that we effectively be getting out to L equals 2,000 to 2,500 in terms of what's happening. Okay, so the Planck satellite is now scheduled for launch in 2009. I'll go more specific in a minute. It also will orbit around L2. We hope it will surpass WMAP in terms of angular resolution, that it should have about 5 arc minutes of angular resolution versus the very best that WMAP had, which was 14, but it was actually worse than that when you do the foreground subtraction, because you have to take longer wavelengths data in order to subtract the estimate. There will be much higher sensitivity to CMB polarization, which Wayne was talking to you about, and there will be much greater frequency coverage, which is important for the foreground separation. So here's an indication of what the sky map looked like in this resolution for WMAP at 2 years and what it should look like at Planck at 1 year. And now WMAP is at 5 years and may get to 6 or 7 by the time we're beginning to publish WMAP data. But still, within a year or two, if Planck is operating properly, it should surpass what WMAP has quite substantially. Okay, so Planck will also map the polarization of the CMB and derive a polarization power spectrum, assuming everything works the way we think it does. So the prediction is this is the temperature angular power spectrum. And you see it starting to blow up when we get down to the L's that corresponds to the 5 Archimedes. And here's the predicted polarization power spectrum for the E modes, which we'll talk about, the EE power spectrum. And this is the predicted error bars. And you can see it starts going a little worse, a little earlier than the temperature does. And that's for a couple of different reasons. But first, the signal is lower. But second of all, the amount of signal we can get in polarization is somewhat different. So Planck is primarily a European Space Agency satellite because the full collaboration with NASA that we had expected didn't materialize, but we got WMAP instead, and so there was something that kept us going on. This will be, the satellite is scheduled to be launched from Kourou in French Guiana with an Ariane 5 rocket. One of the reasons we're late is in order to have another mission, ESA decided to make us go piggyback with Herschel. So here's the Herschel payload, and here's the Planck payload, and we'll see. The people who are participating are very numerous. One of the things that I had hoped that Planck would do, it has been doing. In fact, 2 of the 3 things that I'd hoped for it has been doing. The first, it has made cosmology a much stronger field in Europe. That is, it's brought up the partnership of everyone across Europe, giving a lot of the national agencies incentive to fund cosmology in their various countries. And so you see a lot of activities that way. Simon White's group, for example, gets additional support in principle as a result of collaborating on Planck. But it's true across Europe in general that there has been increased funding for that. The other is, we've been anticipating it coming for so long. We set such a high standard for it. It's created a high standard for the whole field. So now the anticipation of Planck is very great. And so what you'll see is there are 2 instruments that are involved, the high frequency instrument, which is shown in here in the center, and the low frequency instrument, which is shown in sort of gray around the outside. And there is, from California, a very large contingent. There is roughly a 20% contingent to the project. That is, it's 80% European and about 20% American-Canadian. And so a big fraction of those people are from California and from the west coast of Canada, but that just has to do with geographical proximity. Now, the issues are that we're getting down in the situation where there are significant foregrounds and instrumental issues because we're trying to improve on what is already a very good job that has been done. First, good measurement, but with narrow angular resolution by COBE over limited range, and then a very good job by WMAP, and so we're trying to make a significant improvement over that. So we have to worry both about the detector noise, and here we mean not only the white noise in the detector, but the other kinds of noise that show up and that have even been showing up in a significant way in the WMAP data. And if we're going to improve by another factor of 4 or 5 in sensitivity, that noise will show up more substantially. And it doesn't show up just as random noise the way the CMB fluctuations appear to be, or white noise where it's just uncorrelated pixels. You see striping, you see other effects that we was trying to remove. Then there is signal from our own galaxy. These 3 things from our own galaxy, the dust, the synchrotron radiation, and the free emission from our own galaxy that we have to think about removing. And then from galaxies and from clusters of galaxies, we have other signals, some or foregrounds. Some people would consider them signals because they are the Zeldovich effect and so forth. And then finally, we have the primordial CMB anisotropies. And so it depends on whether you're looking to the early universe or the secondary anisotropies to tell you about what's going on. But this is what Wayne was making in his point. The secondary anisotropies and reionizations are things that you must understand well in order to get the science out of the experiment that you need to do. And that's why it was important that Planck measured the sky at 9 frequencies. Originally, there were going to be 10 frequencies, but the Italian Space Agency failed to deliver one of the payloads. They couldn't make up their mind for 2 years, and we didn't have contingency to do it. So there are now in the low frequency instrument only 3 different frequencies. And so here are simulations of what the sky should look like at the 3 lowest frequencies, and then the 3 lowest HFI frequencies and the 3 higher HFI frequencies. There were originally going to be 10, but there are going to be 9. But the fact that there are so many frequencies is going to be important in us understanding the foregrounds and separating them from the signal themselves. Okay, and so here's a piece of information that came from the WMAP claiming that their observations would indicate that the total galaxy fluctuations had a minimum here around the 70 to 80 gigahertz. I think that this is sort of a little pessimistic because the dust variations are much more local, but also they're not as well understood. You see they've used a very simple power law. I believe that it rolls off a little more strongly than that, and then in fact the best sensitivity will be somewhere in this range, but we'll find that out as we make the observations. And these gray bands are the frequency bands at which Planck will be making its observations, and this extra set of bands are shown in here, so you can see how some of them were chosen in order to be able to see the Sun-Zeldovich effect, and Planck should be able to see several thousand clusters of galaxies just from the Sun-Zeldovich effect. Although it won't be able to resolve them spatially, it will be able to detect them individually in order to see what's going on. So this is something that we'll have to see forward to, but this is why you have so many frequencies in your signal. And the question is, how simple, what is the really galaxy fluctuations, right? Some of you may have seen papers by Arcade claiming that radio signals are much brighter than people had thought. Okay, so one of the things that did happen as a result of Ozzy failing to deliver the 100 is we had been trying to scramble to get money to do it some other way. But time got so late, and by the time they made a decision, that we decided to spend that money on putting polarization-sensitive bolometers into making many of the HFI detectors polarization-sensitive bolometers. And what that means is we were in the fact that as time was going on, we thought the polarization became more important. And so what it meant was we were making it more possible for Planck to be able to make polarization measurements. So now all 7 of the 9 channels will be able to measure polarization. And that information, as Wayne pointed out, probes somewhat physically different, somewhat different physics than the temperature anisotropes. It's picking up the signal only from the 1 photon scattering, and that comes mostly from the original last scattering surface, but also at the 10% level from the reionization. And that's why it's so sensitive to reionization, and it's also not so affected by the integrated Sachs-Wolf effect or by the sort of issues if there are fluctuations in the dark energy that will have less of an effect. We hope that will help break some degeneracy. It will also confirm some of the things we know when it's not degenerate. The signal is weaker, and that's why we need the higher sensitivity. And as Wayne pointed out, it's roughly 10% of the temperature anisotropes. And that there are the things we call E and B modes, analogy to the electric and magnetic field, the ones that are the result that are equivalent to having come from a gradient or from a curl of a vector field. And as we know that the B mode can come from tensor perturbations, and if I have time, I will get back to that and say one of the things that we are hoping that Planck will be able to do is have the chance to detect those B modes and understand that. And the thing that Wayne did mention briefly, but we'll presumably talk about again, is that the lensing of the E mode, which comes from the scalar fluctuations, that will put an ultimate limit to how low you can look for B modes, because the E modes being lensed rotates them slightly, or makes them come from a slightly different angle, so can mix the E and the B modes to some extent. So here's a little more history for those that are just familiar with the field, but it's not so important. This was the projected, the temperature E mode angular power spectrum, the cross power spectrum. That is the the amplitude from the E modes against the amplitude from the B modes, and projected for WMAP in blue and boomerang 2K with these red data points, and Planck projected TE power spectrum and so forth. And here you saw before with from Wayne the actual WMAP 3-year TE mode data and the boomerang boomerang 2K actual data for the polarization analyzed in 2 different ways. And without the curves or the squares to guide your eye, it's you know, theory leads you tells you which bends to choose in order to get to sort of the optimum kind of thing. You're already using information to try and do that. But when you get down to the EE spectrum, that is the power spectrum from the E modes, then you see WMAP didn't project to have such a great angular resolution, and you can see what it was in the 3-year data. You know, you might call that a detection or you might not. And the 5-year data is getting to be somewhat more significant. You gain linearly with time. And likewise with, like with boomerang, here is what we project the Planck data should be able to do in order to actually see the E mode peaks quite substantially and so forth. And so here's the actual boomerang data. Again, if you didn't have the curve to guide your eye, you wouldn't be quite so convinced. But it's still something we had to do in order to make progress in the field. And then there's the BB spectrum. And there is a prediction of the BB spectrum you should get from the reionization bump and also from the lensing of the E modes, right? And this is the prediction assuming what might be going on. And here's the existing data on the BB modes. Right? We're not there yet, but that's something that we hope to get to in the next couple of years. So now here's some more recent pictures. So this is a picture I took in February of 2000. Planck was at Alcatel, which is in Cannes, France, and it was being assembled. And so here's the actual spacecraft with the detectors here, and here's the primary and secondary mirrors, which were soon to get mounted on top of this structure in terms of what's going on. So this is to show you the hardware is actually existing. And then here's a picture from the environmental test set up when it was getting ready to go in November. So this is a month and a half ago. And you can see the satellite is assembled. Now you're seeing the back of it, and the mirror is covered in order to keep it clean. It goes in this huge vacuum tank, and it's inside of a closed shell that has super insulation on it, but it also is made so it can be made cryogenically cold so that it can simulate what's like in space. So here's what the spacecraft looks like sort of in artist's conception compared to what you saw there. There is the primary mirror, which is roughly 1.5 by 1 3/4 meters in size. So it's roughly this tall and this wide, and no, this wide. And then the secondary mirror is there, and then the focal plane is in there. And you can see the whole assembly is 4 meters. That is roughly twice as high as me, tall, and it's quite substantial. And these things are the things we call the V-grooves. Here it's called out as thermal shields. We have to radiate away the heat in order to keep the whole equipment cold. And so we do that by having a series of grooves that are V like that and are mirrored on either side. So the radiation from the inside gets conducted out and project out into space. And then there's the spacecraft, the active spacecraft, and there's a solar array because we're into L2, and so we're keeping the sun to our back and 90 degrees away from where the beam is. So here's a picture of the satellite when it was in the test chamber getting ready to be tested. So you can see the scale factor of a human here, or the setup here, where you see the V grooves very clearly without covers on it and the primary mirror and so forth. People setting up to do that kind of stuff. And you know, when I was there, I had to wear the hat, and so I send the pictures back, and they just refer to me as cafeteria lady, because you know. All right, so here's the basic idea of the optics. The beam comes in, of course, filling not all the primary. It's somewhat under illuminated, and the primary into the secondary, and then the focal plane. And the focal plane looks like this. I'll show you a picture of how it was supposed to look. So here's the high frequency instrument, which is all the bolometers, and here's the low frequency instrument minus the 100 gigahertz channels, which are the high electron mobility transistor amplifier systems. So they're coherent detectors. And originally, they were the outer ones were the ones that were polarized, and the inner ones were intensity oriented. But in terms of what happened, we had a conversion of how things went. And you can see that the bolometers are inside, and they're cooled to 1/10 of a Kelvin or slightly lower. And the coherent receivers are on the outside, and they're actually cooled about 18 Kelvin. And that's all done to gain sensitivity. So here's a cutaway of what the high frequency instrument looks like. It's a helium-3 Dewar, and there are these basically back-to-back feed horns with spiderweb bolometers in them and polarization-sensitive bolometers in them, and filters in order to choose the wavelength bands and so forth of what's going on. And all of this is then cooled with a complicated cryogenic system. And here is what the low frequency instrument was supposed to look like long ago. It had some very long wavelength ones out here on the outside where the sensitivity is pretty good, 70 gigahertz, and then the 100 gigahertz, which you saw were missing from the picture in terms of what's going on. And, but this is the two basic techniques. Now, the difference here is you'll notice there's only a feed horn here, and they're all scanning around that way. What you're not seeing is that there is a reference load, which is on the outside of the Dewar for the HFI that runs around 4 Kelvin. So you look at the difference, instead of looking at the difference between two parts of the sky, you look at the difference between a 4 Kelvin reference load and the 2.7 Kelvin sky, only it's not 4 Kelvin, it's close to 3 Kelvin. Right? So they're made to be as balanced as they can. And then when you assemble the whole thing, it gets very complicated because you have the front end where you're looking at the 3 Kelvin loads, and then the 18 Kelvin receivers. That eventually has to go down to the warm electronics, and so there's a very complicated set of plumbing that allows that to happen. Here is the cooling system that exists for what's going on. There is a overall hydrogen absorption cooler that gets everything down to about 18 Kelvin, and then there is a 4K cooler, and then there's a dilution cooler, which eventually gets things down to the 1/10 of a Kelvin through a long sequence of stages. And so you see the V grooves there at different stages, 140 Kelvin, 80 Kelvin, 50 Kelvin, and then you finally have the 20 Kelvin and 18 Kelvin stages. So it's actually a fairly complicated system in terms of thermal, and also in terms of electrical and so forth. So here were our original goal instrument characteristics when we started out, to have the 10 different wavelengths, 10 different frequencies, and cooled to the 2 different stages, and what we're doing. And here is the current set of we're allowed to show current set of what we have and what kind of delta T over T we're getting. So this is delta T over T in units of microkelvin per Kelvin. So that we're getting down towards the 10 to the minus 6, towards the 10 to the minus 6 level in terms of sensitivity. And for the polarization channels, there's generally a root 2 worse than that, except when you get to the bolometers, it's a little worse than that for technical reasons about how the bolometers have to be set up. First, there are fewer of them, and second of all, just the way you have to sort the photons out. Okay, so the launch is going to be on an Ariane 5. So an Ariane 5 is roughly 50 meters high. It's going to be arranged somehow. We drew the straw, and Planck got on the bottom and Herschel got on the top. And so this will be launched from French Guiana, and which is near the equator, so you get the extra boost from the rotation of the Earth. And there's a little bit more structure than I show you here, and I had an animation of that, but I didn't think I'll show that here. So here's the other issue. Here is the Lagrange points, L1, L2, L3, L4, L5, and we're picking the L2, which is in a co-alignment, what's supposed to be shown here in co-alignment between the Earth and the Sun, so that the Earth is back, you can keep your antennas and your solar cells facing back to the Sun, but you don't want to be in the eclipse And so you do an orbit that's around the L2 point, which is a saddle point rather than a completely stable, so you need some station keeping. And so that you're out of the shadow, but you have a pretty direct line back to the Earth in terms of transmitting your data back and so forth. So there's a lot of interesting technical details in this, but it's all just about getting your data, keeping your equipment stable and getting the data back. And so you can see here's just another sketch of what's going on, where you're trying to stay out of the shadow and you're orbiting in this sort of Lagrange orbit that keeps you within 10 degrees of the line of sight back to the Earth and the Sun. So you don't have to move your antenna around. You can just do a relatively simple kind of a situation.
Why do you want to stay out of the shadow?
You want to stay out of the shadow by orbiting around the L2 instead of the... So see, here's cool, right? Because you want to have the sun on your back, right? To provide you power and provide you the warmth that you need. Right? So that's just a simulation showing Planck going out. So the way Planck scans the sky is the antenna is pointing out 90 degrees to the spin axis of the spacecraft, or roughly, not quite 90 degrees. And as it rotates around, it scans a big circle on the sky, which I'll show you in the next picture. So you can see how the beam scans out across the sky, right? Well, light's coming in, but it looks like it scans out across the sky. And with the, so you're keeping 90 degrees away from the Earth and the Sun. Remember, the radiation is coming from the sky, even though it looks like we're painting the sky the other way. But this is just the image building up in our computer. Right. And this isn't the Planck image. This is actually the WMAP image, but that's what we happen to have available right now. Right. And this is almost as good as Martin's simulation. I mean, I'm sorry, not Martin, Simon's simulation, where you saw the simulation, the galaxies moving at many orders of magnitude times the speed of light. Right. This is showing you a year and a few seconds. So depending on what wavelength you look at a different part of the sky. You see a different version of the sky, right? So it's, it'll be interesting to have these all-sky maps in terms of seeing what's happening. Okay, so our current timetable, well, it did say April 10th on the last thing, official thing I've got, but I also got an email 2 days ago saying it was really April 12th. And so we'll see what's going to happen. But right now, mid-April is the nominal launch date. And so there will be scientific data taking, which 18 months was guaranteed, although I think 2 years is pretty much agreed upon just for closure issues. An extension of that is possible. And there's a proprietary period, which lasts for nominally a year, but a year and a half to 2 years after the data is taken where it's analyzed and publications are prepared. And then the data go into the public domains for anyone to be able to analyze that. And all this is still being argued back and forth with people, but that's the general principle of what's going to happen, is that the data become public fairly quickly as soon as it's actually been processed and calibrated and put in a form that's okay. But Simon's group is responsible for doing all this. Yeah, he's okay, so the kind of data analysis that we have to do is fairly complicated. There's a lot of stuff that you don't want to know about. It's like making sausages. You don't want to know how we have to clean the data and find the pointing and mix and get all that stuff to work. But there's a lot of sort of cleaning and calibration and just getting everything together to where you have the time-ordered data. And what we mean by the time-ordered data is the clean, calibrated data plus the pointing information. And that then can go into our map-making algorithms and produce the maps. And when we do that, we should get these 9 maps at 9 different frequencies. There'll be additional maps of other things. And then we go into the component separation, where we're going to try and find the CMB, the various components of signal from the galaxy and from external other foregrounds. And once you have got the component maps, then you want to do the power spectrum estimation. And when you have the angular power spectra or some combination of clean, separated maps and angular power spectra, you'll start doing the parameter estimation. And that will also include polarization maps as part of this kind of a process. So there's a long, complicated set of things that go on in order to produce each of these kind of sequences. And when you look at it, what you see you're doing is you're taking a large number of detectors that are taking a large number of samples per second. So we're talking about something on the scale of 10 to the 12 samples, and reducing that to frequency maps that have on the order of 30 million pixels, and also maps of what the instrument response and systematic effects are that we have removed. Then we're going to divide that into the foreground maps, the point source catalogs, the temperature maps. The point source catalogs then presumably get turned over to people who are making observations on Herschel or on ground-based telescopes and so forth to try and do things with. And we'll have the temperature maps and the polarization maps. There we're getting down to on the order of 10 to the 7 pixels. That is 10 to the 7 individual sets of numbers. And when we get to the angular power spectra, that should give us 2,000 numbers, and if we're lucky on the polarization, 1,000 numbers. And then we want to compress that down to 12 numbers, which are the cosmological parameters, plus some confidence kind of thing. So we're trying to take a huge amount of photons in and reduce them down to a limited number of kind of numbers and so forth. So what science do we want to do? Well, we mostly think we're going to be cleaning up what we've been doing already. That is, trying to determine the cosmological models to a much greater accuracy. And right now we have WMAP and other data, both CMB and large-scale structure, and even some gravitational lensing data, consistent with a concordant model of cosmology with about 6 parameters. That means there's 6 other parameters that we pretty much neglect or just make assumptions about these days. And so we know the physical density of baryons and dark matter, and the cosmological energy density and the dark energy, and the amplitude of the fluctuations. We know that the spectral index and, to some extent, the reionization optical depth, we know those reasonably well, but we're going to try and know them quite a lot better. And what we really are, one of the things we're really looking for is trying to determine the inflation parameters even more precisely than the ones we have now. But you see, we have a very relatively simple phenomenological model now that we're able to use, but it's still able to make a pretty good reproduction of the large-scale structure we see today. And what we do want to study a lot more about the primordial perturbations. So not only the spectrum, but also the questions of the non-Gaussianity and the large-scale anomalies, that is, maybe the lack of anisotropy. Those kind of things that we're going to check, but we're probably just limited on the large angular scale things, but we'll see what we learn over this time period. So you have to remember the progress we made. This is the map that I made in 1992, and it looks a little crude now, but it was startling at the time. And here's another contrast map about how different your world looks, depending on what wavelength you're looking at. If you're looking in visible light, 550 nanometers. This is a picture of Mount Erebus and Boomerang getting ready for launch in Antarctica. And here is superimposed the map of the sky in the microwave background. So your perception of what the world looks like is very different depending upon what wavelengths you look and how far away you look. Likewise, we've been making attempts to try and understand about inflation. And so here are relatively current constraints on inflation models. And these are relatively simple models of inflation, the lambda, phi to the 4th, and phi squared, and so forth. This was from the 2006 WMAP set of papers using all the data from the CMB plus large-scale structure to try and put constraints, what constraints you could put on various models of inflation, although you have to admit that they're fairly simple models of inflation, but we're getting to constrain and limit the various models of inflation that are allowable at this point. And what we can hope is that we can do that. And you'll notice that they're pointing out here these purple spots. They're right at the edge of what's an allowed region at the 2 standard deviation level. And that's the Harrison-Zeldovich spectrum. That is, there's already the claim that there's some slight tilt to the spectrum, which is the sort of thing that you would expect from inflation. But there are other things that we expect from inflation that we'd hope to be able to find in the future. We also still have people clinging to additional interesting possible things in the universe, and some of them would be very relevant. So here's the people saying there are hints of isocurvature perturbations in the cosmic microwave background. If you look, here's the isocurvature stuff down at the bottom, and this is the angular power spectrum, and the slight deviations they're doing, and the fact that they're changed to chi-squared with just 4 extra parameters. And that's true, and as we get more precise data, then that kind of thing becomes a little more difficult. And there's also the interesting question about inflation, is how inflation ends and how it goes. And so here it says cosmic strings and inflation. We certainly think that the majority of perturbations came from some quantum random process like inflation, and they produce the adiabatic fluctuations, and they're the dominant form. But there's still the possibility of adding an admixture of up to 10% of cosmic strings. Those cosmic strings could come from superstrings, or they could come from the actual end of inflation. There could be a U1 symmetry breaking at the end of inflation, leaving cosmic strings behind and producing some of the effect. And so they've tried to do a combined fit to the data. Again, things will get tighter as you go, as you have more precise data out here, but also as you have polarization and other information, we'll be able to limit what's allowed and what isn't allowed. Although it would be extremely exciting and interesting to find a cosmic string, especially if it came from inflation or something else. It would give us an independent measure from the B mode as what was going on in inflation. Okay, so we got some paradoxes. That is, we have a nice model of the universe. It's working fairly well. You're hearing all these talks, people doing the calculations and showing your data, and they work out very well. But we do still have some paradoxes that we hope that we're going to learn something about, that we aren't having this meeting in 20 years and saying, well, we learned a little bit about dark matter since then, on the 20th anniversary. So we had this picture from the early 90s when we were trying to determine whether the universe is open, flat, or closed. And we came with the conclusion, there's a particularly nice picture that Boomerang made, showing that the universe is flat, and yet we have plenty of other evidence showing that the universe doesn't have enough matter, enough baryons, or enough dark matter. And we have evidence from the supernova projects, the Supernova Cosmology project and the High-Z Supernova team, that the universe is beginning to accelerate its rate of expansion, right? And so we have a number of interesting kinds of things out there. And so we have this model that the universe was first expanding the accelerating rate and a decelerating rate, so that we could have all these nice talks about large-scale structure. And then it's expanding at an accelerating rate again. Why is that, right? We don't know. And everybody has suspicions. And we have parameters that we're trying to determine. But one of the things that we have is that somehow the sum of all the energy density in the universe comes out to be very close to making the universe flat, or is what makes the universe flat. And that's sort of consistent with what we expect from inflation, but we don't understand why we have all these different constituents, except it makes things work. And then Wayne told you this morning about polarization, and he gave you the illustration of where you need a quadrupole anisotropy. That is, he gave you the formula for the Thomson scattering cross-section, and it's a dot product of 2 vectors, and that tells you that that's a cosine squared, so it's a quadrupole that you're looking for. So you end up with a linear polarization. And so this is one of the things that we've sort of understood over the last few years to be a very important thing to measure. So again, from Wayne with this slide, talking about trying to measure the various effects. And he showed you this nice figure of the globe with the polarization pattern for a simple large plane wave across that, and talked about the E-mode polarization, the E-mode being the analogy to the electric mode, that is, that comes from a gradient. In that case, if you have just scalar fluctuations, you have only a scalar field, so the only vector field you can produce from it is a gradient. And that gradient field will either point to the peaks and the fluctuations or in circles around the peaks and the fluctuations. So you have a very clear pattern. In order to get something like a B mode, you need an extra angle on the sky. That is, you have to start with a vector, and then when you take the curl of the vector, you can rotate things, you can get circulation. So the gold in here are the E modes, and the blue in here, or the purple in here, are the B modes. And you can see how the pattern looks very different in those two cases. And so we want to exploit this because we know the scalar fluctuations. We know what they have to be because we've seen the temperature anisotropies, and we've seen the first hints of T versus E correlation that we'd expect. We know what level that should be. What we don't know is what could be, what could there be out there producing other things? And the answer is, we know that in fact, in the early universe, if there's tremendous expansion, there would not only be the scalar fluctuations from the scalar field if the inflaton is a scalar, but there will be fluctuations in the metric, and that will produce also scalar fluctuations, vector perturbations, and tensor perturbations. And the vector perturbations will produce the B mode very clearly, and you can possibly see that. But the B modes, that is the tensor modes, will produce both E and B modes in equal amounts. And so we don't expect there to be vector perturbations that survive to the present day. So we think that if we see B modes, then that's a good indication that the tensor modes are there, and therefore the gravity waves produced by inflation and the early universe are there. So we want to look for these patterns, and that is, not only measure the E modes very precisely, but measure the B modes as well as we can. And the amplitude of the B modes will tell us directly the energy scale inflation, and the tilt of the B mode power spectrum will tell us the tilt of the inflation potential at that point. And those are the kind of things that we're after. It depends on how many numbers we can get, how much we can reconstruct from that. And so that's become one of the significant goals for Planck, is to try and measure that as well as we can, and see how well we can do. And so here's the kind of angular power spectrum you would see in terms of temperature. Here's the temperature of the scalar modes, and the temperature variations of the tensor modes if they were equal ratio at the quadrupole, roughly at the quadrupole. But we already know from the observation we have now that the ratio is roughly a factor of 10 down. And so what happens when the tensor modes is they would be essentially flat across this way before they go through the evolution of expansion of the universe. But once they come inside of the horizon, the tensor modes become gravity waves, and then they redshift away the same way the radiation redshifts away. And that's why you see this fall off, and this is the horizon size, basically. And so finding this is very difficult because now we're limited by the cosmic sample variance during this page. So we're already knowing we're down to a relatively low level. So using the B modes or using some other thing to try and measure the gravity waves more directly or indirectly, depending on what your technique is, are the only ways to look for this, or looking for the non-Gaussianities and so forth. So each of the polarization patterns should show up in a different way. The temperature mode, and then there's the E polarization and the B polarization, you see roughly equal. And then there's going to be this is the WMAP kind of estimated errors, and the cross polarization T and E. And then the lensing of the E mode polarization is going to come up down below here, and that's going to ultimately limit you and in terms of what's going on. So Planck will measure the polarization of the C and B with high resolution. So here are two simulated maps based upon what we know of the scale of the polarization. So this is one that tells you the directions. And as Wayne pointed out to you, the polarization isn't really a vector. It's a headless vector. That is, it's a line. So it has 180-degree symmetry. So you don't put an arrow on it. You just have it's a spin 2 particle. But you'll see the sort of pattern you'll see that kind of looks a lot like the instrumental noise I showed you in the early situation, striping and other things, but a lot of white noise. So this is showing you sort of the direction you expect from C and B polarization, and the amplitude you would sort of expect to see, which is at a fraction of a microkelvin, right? It's the kind of level of the signal that you would expect to see from the E and the B modes that we're talking about. So that's the difficulty of the experiment we're trying to get to. And that's not to say that the dust and the synchrotron are not also polarized, and you must take them out in some way. So this is a challenging task that we're after. So we've got a lot of unsolved mysteries. We got to wonder, what is the nature of the dark energy? What is the density of the dark energy? Did we get everything right? And What is the dark matter? These are questions that were asked now for 40 years, right, in terms of the dark matter. And are there some physical effects beyond the standard model of cosmology and particle physics? And what are we going to learn about the future of the expansion of the universe? What's going to be the fate? Is the dark energy fixed, or is it going to change state again, and so forth? So my conclusion is we have some exciting times ahead. This is, the Ariane taking off from cloudy French Guiana. And then here are the 2 satellites on the booster going out and being separated. So Planck is out doing his task. Now, it hadn't quite separated because this is all supposed to be black. Remember, the Planck is, the 3rd generation is fine. It's the stealth model of CMB satellites. It finally looks like a CMB satellite should look right now that we've gotten there. So I'll stop at this point.